Now the W algorithm will sometimes have to solve equations over types. For instance, suppose we want to find the type of an application. E1, E2, where E1 has the type T1 and E2 has the type T2. Then for this to make sense, we must have that E1 has a function type. E1 should have a type T2 to T, because E1 must be applicable to an argument of type T2, because we're calling E1 with E2 as argument. So what this means is that we must solve the equation that T2 to T is T1. So this means that we must find a substitution, sigma, such that if we then apply sigma to T2 to T, then we get the same type as we would get if we apply sigma to T1. And a sigma like that is called a unifier for this equation. Here's an example. Suppose we have the equation that the type expression a to int should be equal to the type expression bool to b. What is a? Well, the unifier that maps a to bool and b to int will work. Sometimes, on the other hand, there is no unifier. Here's an equation. A times int is bool to b. This has no unifier. Why does it have no unifier? Well, because we can never make a type expression which is a product type expression equal to a type expression that's a function type expression. Product types and function types are different. This equation has no unifier. I'm now going to describe an algorithm that will let us find a unifier if one exists, but there is a bit of notation that I'm going to introduce. Sometimes I will write T of sigma instead of sigma of T. So this is a postfix notation, whereas this is a prefix notation, but it's really the same thing. What I'm going to talk about now is the unification algorithm. The unification algorithm, unify, is an algorithm that takes two type expressions, T1 and T2, and gives us a substitution sigma, if and only if T1 and T2 can be unified, in the sense that there is a sigma such that T1 with sigma applied to it is equal to T2 with sigma applied to it. And unify is a recursive algorithm, and it's defined by a collection of clauses that I will present now. Well, here are the clauses of unify. unify T1 and T2. How do we find that? Well, if we want to unify a type variable and a type expression T, what do we get? Well, we get the substitution that maps A to T, but only if A does not occur in the type expression T, because we don't want recursive substitutions. This condition is what is often known as the occurs check. Now, how do we unify composite expressions? Well, if we have T1 to T2 and T3 to T4, how can we unify those? How can we solve this term equation? Well, first we need to unify T1 and T2, so let sigma be the substitution we get by unifying T1 and T3, and then we unify T2 and T4, but we do not unify T2 and T4. In fact, we take T2 and apply the substitution to T2, and T4 where we have applied the substitution to it. Similarly, to unify product type expressions, T1 times T2 and T3 times T4, what do? Again, we let sigma be the substitution we get by unifying T1 and T3, and then we unify T2 where sigma has been applied and T4 where sigma has been applied. How do we unify a type expression with itself? Well, the identity substitution will do. If none of these cases apply, and we try to unify T and T prime, where we're not comparing a function type to a function type, or a product type to a product type, or a type to itself, or a variable to a type, then we know there is no solution. In that case, the algorithm must fail. And we have a very nice result about the unify algorithm. The result that we have for unification is a theorem that says that if S and T are type terms, then it's a case that unify of S and T will give us a sigma if and only if there exists a substitution such that S and T can be unified. Moreover, sigma is the most general unifier. And what do we mean by saying that sigma is the most general unifier? Well, by that we mean that firstly that if we apply sigma to S and apply sigma to T, sigma solves the equation, so sigma is a unifier. But that's not the interesting part. The interesting part is that for any other unifier, say omega, there is a unifier sigma 1 such that the other unifier omega can be found by taking sigma and then composing it with sigma 1. So the idea is that a substitution is more general, is that we can substitute some of the variables in sigma and get omega. And that's what we mean by sigma being the most general unifier. Any other unifier can be found from it. An example of what I mean by a most general unifier. Consider the equation A equals B. Now we could take sigma 1 to be a unifier. It would map A to int, and it would also map B to int. But if we took instead the substitution that maps A to B and B to itself, is also a unifier, and clearly this is more general. Than sigma 1, because we could take sigma 2 that maps B to int, and then we get that sigma 1 is sigma, then applied to sigma 2. First we map both A and B to B, and then we map B to int. So sigma 1 is less general than sigma. Sigma is the most general unifier here.